My name is Fabio, and today I will show you some preliminary results of a series of experiments that were run here in Sheffield and to determine the linkage between the free surface wave patterns and the underlying hydrodynamics. During this webinar, we have the chance to see many practical applications of remote sensing. In fact, they have continuously gained popularity due to the improved robustness and ability to retrieve the characteristics, their facility to use, the portability, and they make use of experimental relation to link the surface with pattern to flow characteristics like the shape of the velocity profile, shear stress, or characteristics of the section like bathymetry or roughness. However, this relation, they do not explain the reason for the existence of the linkage between the free surface and hydrodynamics. So we thought, could coupled and simultaneous measurement of both the free surface and the hydrodynamic give the answer. To do this, a couple of experiments over a bed made of bars were run. So a bed composed by important changes of the bathymetry that, of course, gave a result to important waves. The experiments were run in a 15-meter long and half-a meter wide glass wall flume here in Sheffield. The bars had a side, there were square bars with a side of 25 millimeters and with a Streamwise uniform spacing of 260 millimeters. The slope was pretty high, 1 in 50, meaning that the flow was naturally supercritical. And I don't know if you can see it. I can't for the moment, sorry. Okay. The Manning coefficient was quite high for this type of bed. The characteristics, so the surface behavior and hydrodynamics were investigated using two systems. For the hydrodynamics, it was used the PTV, so particle tracking velocimetry, that is composed by 4 side view cameras. You can see them here, and a couple of blue LEDs that illuminated the flow from the bottom. The traces, they were naturally buoyant traces were used as traces. This allowed it to have a volume of 300 millimeters in streamwise direction, 100 in the vertical, and 280 millimeters in the spanwise direction, and a spatial resolution of 0.14 millimeters in the 3 directions. The surface was studied using DIC, digital image correlation, composed by 2 cameras and green LEDs that illuminated the surface from above. To retrieve the information, of course, buoyant traces had to be used. The field of view was slightly larger than the one that was given by the PTV, but the spatial resolution was approximately the same. And both the systems were run for with 100 to 100 hertz for 3 minutes. This is a screenshot so this is a photo I took with my camera and show you the characteristics of the flow. As you can see, of course, it's made of periodic bars, so the flow is periodic in streamwise direction, and is composed by a sequence of transitions from super to sub to super again, and so on, critical conditions. The hydraulic jump occurred just downstream a bar, and before moving to and after the hydraulic jump, there were supercritical conditions just before another bar, and so change to supercritical conditions again. Another important characteristics of this flow is the presence of important recirculation regions downstream of our water. So using the software for the PTV, this is the result I got. So at the moment you see, well, the tracks and the colors represent the streamwise velocity. Of course, the velocity is the highest in correspondence of the derelict jump, and then it slow down, and in correspondence of the bar. So the gap here is the bar. Just downstream there is a circulation with negative velocities. Approximately 7,000 tracks per frame were used. That is not very high compared to other type of flows, but it was not possible to use a greater number due to the problem of outliers. Nonetheless, some good result was obtained. The tracks were so a bidding procedure was done for using the tracks file as input, and an interrogation window of 80 voxels and an overlap of 75% was used, meaning that the spatial resolution of the measurements was of 2.8 millimeters in the stream, vertical, and spanwise direction. From this file, the instantaneous values were then averaged in two ways. First, the time average velocities were calculated. These were obtained from the sum of instantaneous values in a single cell over the entire time series, divided by the number of observations in that same cell, in the same cell. As said, the statistics, the time average was was computed over 3 minutes. From these, the double average velocity was calculated. So the time average velocity was averaged along the streamwise direction and then along the spanwise direction. So that was just a single value for the entire volume, a single velocity profile for the entire volume. These are the results I got from this time average streamwise velocity. As you can see, the flow accelerates downstream the bar, whereas beneath the below the crest there is the circulation. And from X is the streamwise direction, Y the vertical, and Z the spanwise. Sorry, I should have said that before. Cross and images from above reveal that the flow was there was lateral uniformity. For the time average vertical velocity, it is what is important are the downward motions immediately downstream the bar and upward motions in the recirculation area. Of course, important the vertical motions in correspondence of the hydraulic jump and just upstream the second bar, while the time average the spanwise velocity, well, they reveal that the spanwise velocity was approximately 0 everywhere, and when the time average is in this plot show you the time average velocity, streamwise velocity minus the double average velocity, streamwise velocity. Similarly to the previous plot, it is possible to see an increment of the velocity just downstream the bar, and positive variations, while negative variation occurs in the recirculation. While for the vertical component, positive variation in correspondence of the hydraulic jump downstream the bar, with like a negative variation here downstream the first bar. Again, not much from the Spanwise component. So what can be said that there are, so the flow was laterally uniform and strong upward and downward velocities occurs downstream, downstream and immediately upstream and downstream the hydraulic jump. And there is also a strong upward motion immediately before the second bar. Speaking about the spatial variability, there is a strong Streamwise variability just downstream the bar in the circulation and just above the top of the bar, while an even stronger variability is observed for the vertical velocities in correspondence of the hydraulic jump here and here just before the second bar. Regarding the digital image correlation, it was so the images so it was so the surface was sprinkled by was coated by buoyant traces that were sprinkled from upstream. The traces were polystyrene of 5 millimeters in diameter, and they were used to create spackles. In this case, the subset size was 55 pixel and the step of 15 pixel, meaning that the spatial resolution of this measurement was 2.12 millimeters. Yeah, you can see the reconstruction was possible despite the not uniform coatings. Similar to what was done to the velocity, the time average surface height was computed. These images was obtained using raw data. As you can see, in fact, there are some outliers. The gap here is the hydraulic jump that, due to non-visible misalignment of the camera, it was not possible to reconstruct perfectly. Nonetheless, it was possible to obtain the profile of the surface. Of course, this part is not correct and is caused by the presence of this wrong measurement here. But when the surface elevation is coupled with the hydrodynamics, it is possible to say that where the streamwise acceleration occurs, the surface elevation decreases, and also where the streamwise velocity, decreases. So yeah, the surface elevation decreases where the surface where the streamwise velocity increases, where the opposite occurs downstream the hydraulic jump. In terms of sorry,
1 minute.
Okay, yeah, thank you. In terms of spatial variability, it is possible to see a strong streamwise variability just before the hydraulic jump, while negative variability for the vertical velocity in the same before the hydraulic jump and positive after the hydraulic jump. In conclusion, it was possible to obtain detailed 3D velocity measurements over an extreme topography with bars by means of PTV. It was possible to identify clearly a zone of high temporal and spatial variability. The most critical section were the near surface region, mostly between the bar and the top of the hydraulic jump, and the recirculation zone that extended up to 4 times the bar height. So coupled water surface measurements were obtained optically as well, using DAC, even in poor coating conditions. Both the statistics were seen to follow, to match the result, so the measurement that were taken with both PTV and by means of a point gauge. And regarding the statistics, they vary positively upstream the hydraulic jump and change negatively downstream of it for the streamwise velocity, while the opposite occurs for the vertical averages. the next steps are to run the same type of measurements in more simple bed conditions and with less steep slopes, and to use different type of traces, so smaller like fine sand but buoyant traces, to allow to be able, in this way it will be possible to determine even more accurately the surface position.
Okay, and that's all. That's 15 minutes 30 seconds. So I need to invite any quick questions for Fabio, please.
Just a second. Oh, stop share. Apologize.
I have one if no one else does.
Yeah, go Nick.
Yeah, I'm really interested in this research, and I wonder whether it points, because I'm a field guy, I'm interested in what we can do in the field. So I'm really interested to know from this research, does this point towards, if we want to ever be able to look at the surface to understand the depth and velocity profile, we need to look for certain features on the bottom. So, you know, like a bar or like a rock that's going to create, you know, a specific signature on the surface that we can read for depth.
In this case, it was not, well, it is possible to use also features on the bottom, but in this case, it was possible to reconstruct the surface by means of buoyant particles. So something similar was done in the past with where projected patterns were projected on the surface, but of course that because to do that the water had to be colored. While in this case, and of course that prevented from having PIV or reliable PIV or PTV measurements. While in this case, as the water was clear, was tap water, it was possible to obtain also.
So, sorry, my interest is more in whether you put the bars to generate the surface features. If we're thinking of using these kind of sensing techniques out in the field, should we be looking for river sections that have specific bed structure in order to generate, you know, presumably if we go out to a river that's got a smooth bed, we're not going to get features on the top that we can use to try and interpret the depth from them. But if there are certain characteristic features, like such as bars or boulders, presumably that will increase our chance of being able to determine depth by analyzing the surface structure.
Oh, yeah, definitely. The presence of big elements produce, of course, are quite invasive, so they produce characteristic patterns on the surface. So ideally, it is possible to use these features on the bottom to help the reconstruction, even though it might not be as precise as it could be by using the buoyant traces, mainly because, or otherwise it is possible to have a precise reconstruction, but of course algorithms have to be trained a lot because of the deformation caused by the surface behavior caused by the presence of the feature.
All right, thank you.
Nick, I think that the picture in the background shows it all. There's lots of waves and features on the surface without having bars.
Yeah, no. All right, thanks, Julia.